So in your textbooks, when you've been learning about benzene reactions, aromatic substitution reactions, you've probably learned that benzene acts as the nucleophile, aka it takes its electron density and it attacks something. Okay, well, in this section of the book, we look at, okay, what if benzene isn't the nucleophile, it's the electrophile. It accepts electron density from an outside, very rich electron source. That's exactly what these two reactions are. The one is called elimination addition and the one is called addition elimination. And if you think about it, one elimination happens first, then addition. Okay, and then the other one is addition elimination. So, let's get out some nice handy markers here. Let's go through some criteria that we need for each one. So, for elimination addition, what's going to happen first is you're going to do an elimination and then you're going to add to it. So, there's two criteria that we have that maybe it has, maybe it doesn't. We're going to find out that for elimination addition, you are not going to need an electron withdrawing group. Okay, you just don't need one. However, you do have to significantly raise the temperature and the pressure. So that is, yes, that's a criteria. The opposite is true for addition elimination. For addition elimination, you need to add something first. You're going to go through what's called a Mesenheimer complex, and that you need an electron withdrawing group. And as a consequence of having that group, you do not need high temperatures and pressures. Okay? So now that we identified some criteria, I want to get into each reactive respectively and show why you need an electron withdrawing group, for example, in addition elimination, why you need high temperature and pressure in elimination addition. So for this one first, I want to go through what's called addition elimination. This is the easier one to see. So you need an electron withdrawing group in either the ortho or para position. If you put it in the meta, it just simply does not happen that reaction. So we have this compound here where we have an NO2 group in the para position, okay? And when we react it with sodium hydroxide in heat and then follow it up with an acid neutralization step, what we're going to notice that we get is, well, that bromine was replaced with a hydroxide. Okay, so that's pretty simple, but what's the actual mechanism for this, right? Because it looks a little funky. Like, how do you do nucleophilic attack on a bromine on a benzene ring? Well, this is what we call aromatic nucleophilic attack, or aromatic, SNAR, substitution nucleophilic attack on an aromatic compound. Okay, so let's come over here to draw the actual mechanism for this. So let's start with our NO2 group and our Br, and it's going to look like this. So the first step of addition elimination is addition. So we take NaOH and we heat it up so that nucleophile is happier to attack. We know we heat things up, it's going to slam into the molecule with more kinetic energy. That's going to help this react. So what happens is we're going to attack this center, kind of like how a nucleophile attacks a carbonyl. Here we're attacking a density of pi electrons, and what happens is we push electrons onto that carbon there. So what we get is we're going to get a negative charge, like this, and then NO2, and then like this. So we are beginning to form something what's known as the Mesenheimer complex. Now I'm going to draw a bunch of resonance forms here so you can see it, but basically in the ortho and para positions we're going to feel a slight negative charge. So let me actually just go ahead and draw that out here. So these electrons fold in, these electrons get put on the NO2 group. Okay, So we're going to say NO2. Okay, so notice how there's a negative charge on an electron withdrawing group. This is part of that pool. So I'm going to draw two resonance structures from this one. So the electrons could fold in and put the negative charge on this side, so we could like flip the molecule around, right? And it would look like this. Right? But that's not the most important resonance structure I want to show you. I also want to show you another one where the NO2 group steals those electrons, right? It's going to withdraw that electron density from the ring. So that's what happens here. So let's show that we have a negative charge here and a neutral charge there. Well, these electrons, they're just going to fold into the nitrogen and be given to the NO2. This in turn helps our carbon out, right? So we could put it here. This makes our carbon neutral. But our electron withdrawing group, which can stabilize a negative charge, have that. So we have that there, that complex. This is what we call the Mesenheimer complex. Right here. So what happens next, do you think? So we need to do an elimination now. So we did the addition. We have this Mesenheimer complex. Now we need to do an elimination. So there's actually a cascade of events that occur, right? And it's only felt, it's like if you've ever been in kindergarten, hope you played that game where you put your hands out and you're smacking around like that, and then you smack that way. I forget, it's been quite a long time since I was in kindergarten. But you put your hands out, someone smacks you here, and then you smack your friend, and then they smack, and you go around the circle, and it's the frog by the bank, da-da-da-da-da-da. I forget, been a very long time. But basically, what happens here is they're going to play that game, and basically, and I'll actually use green because it was like frogs at a bank. But look, so this negative charge on the oxygen folds in, which causes these electrons on the nitrogen to fold in, which causes those electrons to get stressed and get pushed onto here, which stresses the molecule, and it's going to say, okay, we're getting overloaded here. Someone needs to leave. It's either bromine or hydroxide. Which one's a better leaving group? Who can abstain a negative charge a little better? A fat bromine molecule or a little hydroxide group? Hydroxide could do it, but if we do that, we just go right back to where we started, right? So there's an equilibrium. However, if we kick out the bromine, for example, we're going to get a new compound, and that's the compound of interest. So we kick out the bromine. Bromine's the winner here. And we're going to get the following compound, and you're going to notice that's our product right there. So I actually draw out all of these here, but notice we got that product through that Mesenheimer complex game that they played, and we got that. Pretty cool, isn't it? So that's addition elimination. You need an electron withdrawing group because all this negative charge on the ring is not good, very not good. But if we have an electron withdrawing group, it can kind of lower that charge, right? So there was a charge in the para position on that nitrogen carbon. Nitrogen just stole it, okay? And they can better handle that. That's why we are favored for an addition elimination when we have an electron withdrawing group. You do not need to raise the temperature and pressure to any really significant amount. You do have to heat the solution, but not to what we're going to see with elimination addition, extremely high temperatures and pressures. Okay, so we want to know what happens in an elimination addition mechanism. Why are we heating this up to such crazy temperatures? 350 degrees Celsius is about what this reaction would occur at. Why? Why does it have to do that? Well, remember from organic chemistry 1, you've probably, or just even general chemistry, you learned about this distribution of electrons where we said, okay, percent of molecules over their temperature, right? So a very small fraction of molecules are moving at a very, very, very high speed, right up here, right? So when we heat molecules, we take the average. So this is the average kinetic energy of all the molecules. Now when we heat molecules up, we know that they're going to collide with a molecule at more of a speed, more kinetic energy. That's going to provide activation energy, and if we have that, we know that some reactions can occur, even extremely unlikely ones, if the molecules are moving fast enough to make such an unlikely reaction occur. And that's what happens here, right? We're going to see a very unlikely reaction occur. So we have a hydrogen here and we have a bromine, okay? So one of the NaOHs is going to be running super fast. It's going to slam right into the bromobenzene, and it's going to steal this hydrogen, okay? And it's going to eliminate onto a double bond, and we're going to get rid of the bromine. Now this is where it gets really, really weird, is we get, you're probably wondering, how the hell do I draw the resulting compound? Looks like that. All right, we call that a benzyne. This is a benzyne, right? Benzene, add a triple bond, it's benzyne. It's really, really strange, but that is a real molecule, and there is evidence for this, which we'll get into. It does you can do a trapping reaction, but we'll look at that in a second. We need to actually finish the reaction. So we did the first part, we did elimination, okay? We did elimination. Now we have to do the addition. So it starts with a nucleophile coming in, right? And it's going to attack either side. Now this is a symmetrical molecule, so it doesn't matter. So the OH comes in and attacks this carbon, for example, and is going to push electron density onto one of the carbons, and it will leave us with a really, really, again, this is a very cursed reaction. We have it here. Okay, so we have a negative charge here, and simply water just comes in next, right? Because here we made water, so we do have water in solution, right? And it's just going to pick up a hydrogen, and we will get our resulting phenol. So we went from a bromobenzene to a phenol by elimination addition. And we didn't need an electron withdrawing group. So if you just have benzene or bromobenzene to start, you could simply convert it to a phenol if you really need it, although that would be a very big waste of money. In my opinion, phenol is a lot cheaper than bromobenzene, I can only imagine. So evidence for elimination addition, that we actually go through this benzyne, is, okay, we're going to add some furan in there, and we're going to see if a cycloaddition happens. Remember, in Diels-Alder, the 4,2 addition reaction, also known as Diels-Alder, we know that this reaction, basically these electrons push out to this carbon. It's going to cause these electrons to push down onto this bond, and then these electrons are going to come out and make a bond. So we get this nice little molecule. And then we're going to get 1, 2, 3. Okay. So we get that little addition product that looks like a benzene fused with a furan, and that can only happen if we make benzyne. So that is evidence there that elimination addition goes through that benzyne intermediate. I just thought I'd throw it in there, and I'll actually link the paper in the description if you want to check it out. Hope you guys enjoyed. Hope you learned something today. That was addition, elimination, and elimination addition. If you have trouble remembering the two, just kind of in your head go through the mechanism, okay? If it says elimination, you know you're going to have to go through that benzyne. You can't do elimination on a benzene that has double bonds unless you go through a triple bond, right? But if we go through addition first, we add, and then we have a single bond, so then we eliminate. Pretty simple. Hope you guys enjoyed. Have a wonderful day.